Okay, welcome back. Happy Monday. Our quick look at the calendar tells us that today we are talking about population growth, and in particular, everything we do today will be linear, which will be contrasted on Wednesday, where every kind of growth example we look at will be exponential. So today we're going to kind of piggyback off of the notation we looked at for sequences last time. And another note coming up on Wednesday, November 5th, what's happening here? Projects are due. I still have only received one project. These projects are going to get emailed to me when they're done. I did have a couple people ask questions about them, so that's good because questions means people are working on the projects. So the project is due Wednesday. Again, there's a variety of resources on YouTube and on Moodle, so use those resources as you work on the project. I do take projects late, but there are various lateness penalties. You can look them up on the syllabus. Any questions on the calendar? Okay, and then just one thing, not about this specific calendar, but I've written two notes here on the sideboard. Tomorrow, Tuesday, is Election Day. Get out and vote. A reminder, I will give you 5 points on your project coming up if you prove to me that you went out and voted. Take a picture of yourself next to the building that says vote here. Just something. Let me know that you went out and voted. Again, there are going to be 4 questions on the ballot, 4 yes/no questions. It took me 5 minutes to learn about these questions and make a decision about how I feel on each of these questions. So it's not a big investment of time. So let me know if you don't know where to go, but it's that same site that we projected a few classes back. Also, tomorrow is advising day, which means there are no day or evening classes here at GCC. Zeke, shh. There are no day or evening classes here at GCC tomorrow because we want you to have the opportunity to meet with your advisor. Tomorrow is the first day that you can register for spring classes. If you don't know who your advisor is, see me right after class and I will tell you. And if you do know who your advisor is, just go to their office and write your name on their little schedule. They probably have a bunch of availability tomorrow. And you could meet them on Wednesday or Thursday or Friday, but just tomorrow is the first day. All right, any questions about tomorrow? Okay, so 36 starts with a bunch of vocabulary that we're actually going to kind of skip through, but anyway, it's here. We might refer back to it in a little bit, but I just want to jump in with the first problem, which is number 6. So let's see, can we get Sam to read number 6? Okay, so we're going to write down recursive and explicit formulas for P sub n. P sub n is going to be a generic name for the amount of radioactive waste in the tank after n years. So the first number in our list is actually going to be P0. Sometimes it's called P1 as the first one, but for everything we're doing today in next class, we'll start with P0. So P0 is the amount of stuff in the tank initially. 0 is the initial part. How much is in there initially? It's 35. And then let's go ahead and write down the amount of stuff in there at the end of the first few years. So how much is in there after 1 year, which is what we're saying is P1? It gains 5 tons every year. 40, right? Just 5 more than the initial amount, so 40 tons right there. And then P2 tells you how much is in there after 2 years, 45. And then P3 is the amount after 3 years, and that's 50, okay? So we've seen this notation before. The subscript last class would just tell us which number in the list we were talking about. This class, it specifically says, hey, just look at year blah. Year 3, 50 tons of waste in the tank. Super. So now what we want to do is we want to go from the very specific list that we've got here to a very general, a very abstract idea, and that's what's going on in year n, a variable year. Okay, so first we'll do the recursive formula. So what was the general idea, like whenever we had recursive things, what would be the next thing after this equals? P, and then what was down here? n-1, do you guys remember that? It was like almost every single one of our recursive ones looked like that and then something else. So this equation isn't true at the moment, but it says if you want to know what's happening in a certain year, you look at what you had in the previous year, in 1 year earlier, and then you do something. What is the do something every year? Is you add 5. And so that right there is our recursive formula. And again, I need you to be able to see what that means in English. Don't get lost in the symbols. It says if you want to find out what's happening any year, you look 1 year prior and you add 5. We weren't very careful about this last time, but technically you can't just have the recursive formula without telling us how much you have initially. What did we have initially? It was 35. So actually those two equations together are our recursive rule, right? It's not enough for me to just tell you, hey, it just gains 5 every year without giving you a starting point. So recursive always has two different pieces of info given. Okay, so that's fine. And now let's see if we can write down our explicit rule. Okay, so the explicit rule would say we started with how much stuff initially? 35. And then we know we gained 5 every year. But yeah, to make it happen every year, not just once, tack an n on at the end, and I think we'll be able to see that that's the formula that's going to give us the answer. So for example, if we wanted to check, we could find what P3 is according to, I'm just making up the 3. We could use that equation to see if P3 that we get agrees with what we know P3 is. We know it's 50. Let's see what we get here. This would say 35 plus 5 times n is now 3. So 35 plus 15 is 50, which is what we expected it to be, right? And so there's something very powerful about that formula, because that formula will give you the amount of stuff in the tank at any time without finding the previous few years, right? If I wanted to let this run 10 years down the road, I don't have to find the first 9 years if I'm using this formula. I can just plug n equals 9 in directly. Does everybody understand this plus 5n? That's kind of the key to the explicit formula. Let's see, so I'll circle here. The explicit is this guy. Okay, good. Let's go to Ashley for the last part, the 5. Yeah, so we're defining that phrase common difference. Every year you add 5, meaning the difference between any 2 consecutive years is always 5, right? Okay, next page, number 7. Let's go to Eric. Okay, so let's see if we can figure out what's going on here. So normally we start with P0, P1, and P2, but unfortunately we don't have any of those numbers given to us. And we also aren't given the rule that said something like add 5 every year. So I guess we could start with, this is the first number in the list that we know. P3 is 28. And then I'm going to go ahead and write out the next few, even though we don't know them. P4 and P5, unknown, but P6 is 40. Okay, so there's an important word here that allows us to get started, and it's this word linear. Linear growth model means you are adding the same number every time, or subtracting. Addition and subtraction are pretty much the same idea. So our job is to figure out what we're adding every time in order to get 28 to build up to 40, but it's got to do it in the right number of steps. So how many jumps are there from this third number in the list to the 6th number in the list? Is it 2, or is it 3, or is it 4? How many times is 28 going to get added to build up to the 40? It's 3. And we can count them here. So the first leap gets us from 28 to P4, right? I don't know how much I'm adding, but I'm adding something. And then the next one gets me to P5, and then the next one gets me to P6. Everybody see there are 3 jumps that are happening from P3 to P6? And hopefully many of us are thinking there's some natural thing to do with the 40 and the 28. What do we do with those? Subtract them, right? Got to figure out how much we jumped by total. So we'll take the 40 and subtract the 28 and get 12. And we know there's 3 equal jumps in that 12. So what's the operation? It's 12 divided by 3. Yeah? So that means that our, what do we call this here? Common difference is what we're calling it. Is the 12 that we got up there divided by the 3. I'll put this 3 in green so we associate it with the number of steps that we took. We jumped up 3 times and landed on 12. So they must have been 4 each. Are questions on the process? So hopefully that's pretty intuitive for most, if not all of you guys, because I haven't written really any formulas out. It's just kind of thinking it through. Okay, so I think we've got the info we need. The common difference here is 4. So let's go ahead and write down our explicit formula. We'll do that one first. Pn equals. Okay, what do we start at in this list? What are we starting at? Do we know what we're starting at? We don't. We don't have like the 35 tons initial amount. So I guess we're not really ready yet to get the explicit formula. I know we jump up by 4 every time. Could we work backwards from that 28 up the list? Okay, so let's go up the list now. So 28 was this number, so the previous one must have been 24, 20, and 16. Okay, that's helpful to us. So 16 apparently is where this list starts, even though we weren't told that initially. Okay, so we start at 16, and then we gained how much every time? 4. And how do we make it so that it's a 4 every time? It's 4n. And in doing 2 of these, hopefully we're starting to kind of see that this explicit formula always follows the same general idea. That 16, what was it called? That's the starting amount, right? We started at 16. What is the 4 called? 4 is the common difference, and then n is just our variable. That's our counter. Okay, so that's our explicit formula. And let's go ahead and also write in our question. Zeke. Yeah, so there is a nice way to think about this in terms of lines that maybe you guys have a lot of practice with, but if we wrote this as 16 plus 4x, or if we want 4x plus 16. So this is not part of this course, but it's something that I think many, if not all of you have seen before. So what is that 16 called? Yeah, that's the y-intercept. You guys remember this? Y equals mx plus b. Ingrained in your brain with lots of question marks. What's the 4 called in line language? Slope. Yeah, and it makes sense that the 4 represents the slope, because the slope would literally mean every step you take to the right, you got to jump up by 4 to get back on the line. 1 to the right, up by 4. Well, that's exactly what's happening here. Every time you go down this list, you better go 4 up. And the 16 is the y-intercept. Makes sense as well, because that's kind of like where the line starts. Technically, it goes forever both ways, but oftentimes we kind of think of it starting on the y-axis. Yeah, that's good, Zeke. All right, so recursive, just about every time starts Pn equals Pn minus 1 and then something. So we'll start it there. And the basic idea for this list was that we keep adding what? 4. So it's just a plus 4. And that's it. And I want to point out that there's a real big opportunity here to make a mistake, because the explicit one has a plus 4n, and the recursive one has just a plain plus 4. And so you got to keep them separate. You got to know which one has the n attached to it and which one is just alone. And like we mentioned before, the recursive technically now has 2 pieces. It has the kind of general rule, but also the starting point. In this case, it's 16. Okay, number 8 says you don't need to memorize these, but here are the general formulas for a linear growth model. Anytime you see in the homework or on a test, linear growth model, it's this kind of phenomenon we've been looking at today. So recursive always has 2 parts, P0, which is just our start amount, and then our generic recursive rule is here. So we've seen Pn equals Pn minus 1 many times, and then you just tack on plus the common difference, right? In this case, we added 4 every time. For the waste problem, we added 5 every time. And let's make sure that the explicit formula also matches what we've seen. So do these two guys look the same? Says Pn is the start amount, that was 16, plus n times the common difference, n times 4, probably more commonly written as 4n. Okay, let's go to number 9, Matt. Okay, thank you. Part A says how many widgets will the manufacturer have on hand after 20 weeks? Okay, so 2 choices here. You could either list all of these numbers out, like the initial number here is 387, and then the next week we have 37 more, and the next week we have another 37 more, and you could just do that like 19 or 20 times. Or we could use the explicit formula, which is the better tool in this case. So it says Pn is equal to the start amount plus n times the common difference. All right, so Pn equals, what's the start amount here? 387 plus, and then we've got n times the common difference. How much do we gain each week? It's 37, so this will be plus 37n. Okay, and in part A, what do we do with this 20 in my formula? Right, so really we're just substituting in, right? Okay, so then substitute n equals 20. So that formula becomes P20 equals 387 plus 37 times 20. And we'll crunch some numbers. 387 plus, what is that, 74? Seems good. 1127, it's okay. All right. Part B, I think I actually jumped the gun a little bit here. It says, how many will the manufacturer have on hand after n weeks? Write both a recursive and explicit formula. What did we write up there? Is that a recursive or explicit one in purple? Yeah, that's an explicit formula because it doesn't refer to the previous year. It doesn't refer to the n-1 element in the sequence, but just directly explicitly refers to n. So we've done that part already. That's that guy. But the recursive one we don't have yet, so let's get that one written down. How do we start all of our recursive formulas? Okay, so that's how we begin. And what was the rule every week? Do what to the previous number? Add 37. So that's exactly what that says. And the only other thing we need is the starting amount at 387. So those two things comprise the recursive formula. Questions on the two formulas? Okay, part C. How many weeks until the manufacturer has 720 widgets? 720 widgets. Where do we put that 720? One vote for PN. We got that purple formula, and the 720 has to go someplace in that purple formula. Where does it go? Does it go to PN or does it go for N? It goes for piece of N because that left-hand side, that piece of N represents how much stuff you have, how many widgets you have in this problem. So we'll just substitute the 720 for the piece of N. So this guy, I'm gonna have to scroll it off the screen, but we're just putting a 720 equals, right? Copying everything there. seeing if you guys are paying attention. 7N. Good, thank you. Okay, so now, like for the first time all semester, algebra. Okay, so it's 2 steps. Write down the 2 steps and solve that equation for n. Okay, so I think folks got rid of the rust, right? Subtract 387 from both sides. And then what do we get there? 37n equals 333. And then do what to both sides? Divide by 37. Magically 37 goes evenly into 333. And we get n is 9. So after 9 weeks, we'll have exactly that number of widgets. Hooray, algebra. All right, let's move to number 10 on the next page. Okay, our reader is Jen, and Jen, I'm going to give you a hint. When you get to this word, it's pronounced arithmetic. All right. Good, arithmetic sequence. Okay, so like this list right here, 16, 20, 24, 28, that is an arithmetic sequence because we're just adding the same amount over and over, right? Good, let's go to 11 in the back. Yeah. Okay, so I know that some people are really good at the problems that we've done so far. I suspect that this would be the first problem that will challenge everybody in the room. This is a tough problem. We've got to figure out how much we're going to spend on widget storage altogether and over the course of 2 years. So let's just get a few of these numbers up. P0, P1, P2. We haven't written these down for the widget problem yet. What's the initial amount for the widget problem? How much are we storing? How many widgets? 387, that was how many we had at the end of initially. And then every week we gain 37 widgets. Everybody okay with where those numbers come from? We just add 37 every time because that was part of the widget problem. And we didn't really need these numbers before, but I think we need them now. Now this keeps going until, what's the last one that we're interested in for this problem? Zeke says 104. Somebody not Zeke, explain where 104 comes from. Jen. Okay. So 2 years is 104 weeks. So P sub 104, that's the last number that we care about, right? So at the end of 2 years from now. Okay, P sub 104. All right, I don't want to fill in the first 103 of these numbers to figure out what P104 is. So somebody we haven't heard from yet, how are we going to find this without filling in all the missing numbers? Yeah, we got a formula, right? We wrote down a formula for how to find the number of widgets in any week. It was 387 plus 37n, right? And in this case, it's not n anymore. What is it? It's 104. And so here's a reason that we want that formula. It's that we don't want to have to fill in 103 pieces of information to get this one, the only one we care about. So we use the explicit formula, which explicitly lets you get whatever number you want without doing previous calculations. Okay, who's got this number for us? Anybody else confirm that? 4235? Good, thank you. Okay, so this is how many widgets this person has at the end of each of the first 104 weeks. Now, how much does each widget cost in storage? $10. So what are we going to do with this 387 to find out how much we spent on storage in that first week? We'll multiply by 10, yeah? So I'm going to just make a column over here that's like, I guess weekly costs is what it is. So we know 387 times 10 gives me $3,870. This widget storage business is expensive. Okay, so that's how much we're going to pay for that first week, right? The initial week. Yeah. Anybody know what a widget is? Yeah, it's just a generic name for some kind of contraption. Yeah, anything. Okay, and then in the next week, we're going to multiply what by 10? The 424 by 10. That's $4,240. I feel like I chose the wrong line of work. I should store widgets. Like I should just like get paid $10 a week and hold this guy's widgets for him. Yeah. All right, and then we'll do one more of these because it's so much fun. 461 times 10, that's $4,610. And let's do the last one as well. So dot, 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 and then what are we doing in the last row? Yeah, so we're going to multiply that blue 4235 by the same 10. 42,350. I could like buy an island in the Caymans and store these guys' widgets for them. I'd still have money left over. Okay, so these are the weekly costs. How do we find the total cost? Somebody we haven't heard from yet today. How do I find the total cost? We're going to add them, right? We need to add those numbers. How many numbers are in this list that we're adding? There's 104 numbers in that list. So number one, I don't want to have to like actually type them all into the calculator. Number two, I don't want to actually calculate them, right? We haven't even found most of these 104 numbers. We just found 4 of them. So we need a different technique. We got to do something better than like brute force add these 104 numbers up. Zeke. Yeah, so Zeke has some fancy formulas that he's bringing up from his past. So this right here is the Greek letter sigma. It's their capital S. And so this is going completely beyond what we're drawing, like what we need for this course, but we've got this notation. So in case you've seen it before, you could say go from I equals 0 to I equals 104, and then you need a generic formula for the thing that we're adding, and it's this 387 plus, what was it, 37? We called it N, but in this formula it's an I. So there is a compact way mathematically to add up these 104 numbers. We're not going to use it, but there is a nice way to write it up. So there it is. Thanks, Zeke. It's not me. Yeah. Okay. So what we're going to do is something that's really fancy, actually. It's easy. So here it is. What would you guys? Let's see. How to say this? Would you guys agree that in this list of 104 numbers, there's like one number that's in the middle, or there could be 2 numbers in the middle, depends on how many, but there's like kind of an average number in the middle, right? Like the cheapest week is the first one and the most expensive week is the last one, but they kind of average out to whatever the middle number is in this list. And then the second most expensive week and the second least expensive and the second most expensive would also average out to the middle. So the idea here is that we don't actually need to do all the calculations. We can just pretend that all of these numbers are like the average of all the numbers. So here's how we'll do that. We are going to take the first number and the last number, and we're going to add them up. And how do you find the average of those 2 numbers? Divide by 2. So let's add those 2 numbers up and divide by 2. So I'm going to write this under total. Total is equal to, so we add the 3870 plus the 42,350, and we're going to divide that by 2. And we get 2, 3, what is it? Okay, so 23,110 is the average cost in any given week. But basically, we can pretend that every one of these costs is just the average. They're all 23,110s. So the only other thing we need to do is figure out how many of those numbers there are. This is the tricky part. How many numbers are in that blue list over here? Starts at P0 and goes to P104. It's 105. Yeah, it's that little twist, right? Because if I got rid of this P0, then the first number is the 424, and the second number is the 461, and the 104th number is this bottom number, right? So would you guys agree there's 104 numbers in this list after I've crossed off the P0? And then we bring one more number into the plan here, and it's 105. So we're going to multiply this whole answer by 105, and that's going to be it. Jen? Yep. Jackie? This is our answer. The average is part of the calculation. You multiply the average by the 105. Sam, what do you have? Okay. $2,426,550. That is the total of all of those numbers. This is a lot of money. Okay, so number 12 actually gives us this formula like it's written out, and hopefully it'll be pretty easy to read. Zeke, number 12. The arithmetic sum formula. That's what we did. We added the first term and the last term. That was this 3870 and 42,350. Multiply by the number of terms, this 105. The notes are written right now so that you divide by 2 at the end. You're also welcome to divide by 2 in the middle, like finding the average explicitly, and then multiply by the 105 last. So this is the toughest thing we've done today, and we're going to do one more of them right now. You're thinking like an even odd type thing? So if it's linear, it's always going to work. Linear, it always works. Right. Yeah, any linear thing we can add them up by doing this technique. Okay, so let's look at 13, and we'll go over here to Christopher for 13. Okay, so this problem we're going to do without using our fancy formula, and then we're going to use the fancy formula to make sure that it gives us the right answer. Because I suspect probably some folks here aren't still quite clear on why the formula works, and I don't want to just like bully you into thinking that it works. I want you to see that it works. So let's try one where we could actually just do it. 5 numbers is not that big a deal. P0 in this case, what's the initial amount of waste? 35. And then it's P1 and P2. P3, P4. Now what are we doing here? Over the next 5 years, right? So I think that's the end of it. Is that true? P0 to P4 is a total of 5 numbers there. So that should be over the next 5 years. Okay, and we know we're adding 5 every year, so we can fill in 40, 45, 50, and 55. Just like we had weekly cost up above, we can do yearly cost right now. Yeah, so you have this 35 tons of stuff in the beginning, and it's a great question because it's not clear when the 5 tons gets added during the year. We're going to assume it happens at the end of the year. So if we did go another number, it would be answering a different question. I think that we're answering the question as it's laid out here. It says over the next 5 years. So from 35 to 40 is the first year, second, third, fourth, and I think this is answering this question. I think if you did one more, it would be 6 years worth of storage. Okay, so what are we doing with these things to figure out how much it costs? 35 times 1,000, right? So we just hit each of those with 1,000. 35,000 and 40,000. And then we'll get the total down here. And like I said, there's only 5 numbers in this list, so we can just add them by hand or with a calculator. We don't need any fancy formula. So let's just add them by hand or on the calculator. Is it 225000? Okay, so we just add them brute force. But now let's see if that formula, that the confusing formula was from above, gives us the same answer. Yeah. Okay, so what the formula says is you add the first and last numbers. So we say or. So we add the first and last numbers, 35,000 plus 55,000. And the formula up there, the paragraph says multiply by something. For me, I'd rather think of averaging this guy right now. So what do we do with these two numbers to average them? Divide by 2, right? That finds the average. And then we multiply by the number of terms. How many terms are in that list? 5 numbers in that list, right? Well, let's actually look at the little details of the calculation. When you average 35,000 and 55,000, what do you get? What number is halfway between 35 and 55? It's 45. So what this is saying is it's 45,000 times 5. Okay, so if you just type that in the calculator or do it out by hand, you'll get 225,000, the same answer we got before. But I really want us to buy this formula as being something reasonable. Instead of thinking of these as 5 different numbers, I can replace them all with the average number. What's the average of those 5 numbers? 45,000. And so I'm just going to pretend that I have 5 copies of 45,000 up there in blue. Do we buy that? That that's going to be the same sum as blue? Because how much over the 45,000 is the 50,000? How much over is that? That's from here to here is 10,000 over. But how much under is the 35,000? Is 10,000. And so these two guys kind of like the amount that one is over is the same as the amount the other is under, and they kind of cancel out and meet in the middle at 45,000. And the same thing for these two numbers right here. Having a 40 and a 50 is the same as having two 45s, right? Add them up, you get 90 either way. Yeah, Dave. Exactly. So like in theory, you can add as many numbers as you want, but in this previous example, I didn't want to add 105 numbers. So the formula is much more useful when there's a lot of numbers. Questions on that? Okay, real quick detour before we look at the activity. There was a mathematician back in the 1800s, Carl Friedrich Gauss. We don't do very much history in this class, so here's a little 2-minute history thing. Carl Friedrich Gauss was a German mathematician, lived in the 1800s. And when he was a boy, he was, like 8 years old or something in grade school over in Germany. And the rumor has it his teacher had a late night one night before classes. And so it really wasn't like up to giving his standard classroom thing. And so he gives the kids busy work, right? You guys have had busy work assigned to you. So he just gives these kids busy work and he says, okay, kids, you're going to add these numbers up, 1 and 2 and 3 and 4, and all the way up to 100. Now, back in the 1800s, they don't have the fancy notebooks that you guys have. they have like little slate, like chalkboard type things and some chalk. So like as you do these calculations by hand, you'd have to kind of be constantly erasing this stuff. You wouldn't have a record of everything. So you'd really have a lot of like navigating to do because you just have this little slate that you're using chalk on. And they don't have the calculators back in the 1800s either. And so it's really all by hand. And so he expected that he'd, like the little kids would leave him alone for like at least a half hour, maybe more. And probably nobody get it right because there's a lot of arithmetic to do here. And so he was really surprised, the teacher was, when this one kid, Carl, writes one number on his slate chalkboard, like immediately, right after seeing the problem. He just writes one number on the chalk, on the slate chalkboard, and walks up to the teacher's desk and puts the slate face down on the desk and walks back to his chair and sits down. And the teacher flips it over and is quite surprised to see the right answer. So first, how did young Carl Friedrich Gauss do this without doing all the calculations and without doing anything on a calculator? It's a formula. So what's our nifty little way to do this now? How do we do the actual calculation? 1 plus 100. Divide that by 2. Multiply by, how many numbers are in that list? I think it's 100 numbers in the list, yeah, right, from 1 up to 100. Okay, again, we don't have calculators, and so maybe the best bet would be to reduce to, right? And so this is really saying 101 times 50. And so there's 5, and there's 0, and the 5, and then one more 0 at the end. And okay, so like it's easier for us to look at that and we'll say, well, yeah, it's not that big a deal. It's not very hard to do this, right? But Gauss wasn't shown this formula, and he was 8 years old and just like instantly figured out how to do this on the fly. And he was a real, yeah, he's not a fan of busy work. But he ended up being arguably one of the top 3 mathematicians of all time. And this is kind of a nice story because at this moment, the teacher realized what a prodigy he had in front of him and directed him to people that were more capable of handling young Gauss's genius. So he did lots of stuff and went on to be very famous as about 8 years old. Yeah. Okay, so that is our little history tidbit. Next page, case for wind and solar. Solar is the activity. Raise a flag if I can help. And if you finish this early, you have half an hour, you might be able to finish this and then get a jump start on tonight's homework.